The quantum theory of matter is now about 100 years old, but to really get a feel for how radical it was at the time that it was introduced, it's useful to look back a little bit further than that and see what the state of our knowledge of the world was before the quantum theory came along. And a very good illustration of this is blackbody radiation, and we'll talk a little bit about what that is. But let me first set the stage by indicating that back around the turn of the century, and by that I mean the turn of the 20th century, so from 1899 to 1900, classical physics had a few very fixed ideas about how the universe was organized. First of all, we thought of matter as being entirely consistent of particles. That is, little finite things that had mass and that obeyed things like Newtonian mechanics. So the classical physics of Newton were essentially what governed all of the physics of these things. So things like the force is equal to the mass times the acceleration, things like that. We also, at that time, had a pretty good idea about light, and that was actually more recent than Newton's work. We had a good idea that light behaved like waves, and this was due to some work that James Maxwell did. And for those of you who are familiar with the name Maxwell, it is the same Maxwell that's involved in Maxwell-Boltzmann velocity distribution and so forth. But that Maxwell did a lot of work in the theory of electromagnetism and basically showed that electricity and magnetism were two versions of the same fundamental force. A third area in which classical physics had something to say was energy, and basically held that energy was a continuous quantity. That is to say, an object could have any energy. It was not restricted in the energies that it could have. Now, in order to understand where some of this began to break down and to understand blackbody radiation, let's first say a little bit about what a light wave might look like. All right, so what I'm going to draw is a little coordinate diagram here where we'll have a spatial coordinate x, and a light wave might be something that would oscillate like this. And so you can see that it is an oscillatory function that goes back and forth here. And we can define different things on this function. For example, this distance between successive peaks is something that we would label as a wavelength. All right. And we would also specify, for example, the height of these peaks is something we would call the amplitude of this wave. All right, so these are things that help us quantify what a wave is like. I'll also mention that it will, typically move in time. So this oscillating function could move from left to right, or it could move from right to left, either one. And it moves at a velocity that we know now as the speed of light, which is roughly about equal to 3 times 10 to the 8th meters per second. All right, so all of that was reasonably well understood. Now, I want to specify another quantity here, and that is the frequency. Okay, the frequency of a wave. It's related to the wavelength, but it's basically the inverse of the wavelength in some ways. Basically, a frequency is how many oscillations occur per second, or pass per second. And we typically give it the symbol Greek letter nu, which looks like a funny looking V. All right, this Greek letter nu. Now, one way to think of this is if this wave represented like a train, okay, with different cars attached like this, and it's moving from left to right, what the frequency is doing is it's counting how many cars pass you per second. So how many oscillations pass a given point, so let's say this is the point, how many cars are going to pass per second. So it has units of inverse seconds, okay? And one way we can relate this to the wavelength is we can say that the frequency is going to be equal to the speed of light divided by its wavelength. All right, the wavelength is telling us what the difference is between these train cars. The speed of light is telling us how fast it goes. So the frequency that they'll pass is going to be the speed of light divided by the wavelength. We could also write this equally well as the wavelength times the frequency is equal to the speed of light. Okay, and we can justify this all. We can say that the wavelength is going to, for example, have units of meters. The frequency is going to have units of inverse seconds, and so the speed of light would have units of meters per second. So you can see that when we multiply these two together, we should get the right units. All right, now what about black bodies? Okay, what is a black body? It sounds very mysterious and contrived, but essentially it's just a physical object that has a definitive temperature. So physical object with a well-defined temperature. Now we need it to be well-defined because essentially what's going to happen is that as you heat an object up, it begins to emit radiation. And in fact, we know that hotter bodies are going to proceed through a series of colors. And this is something we know from our own experience that, for example, as it gets to a certain level of heat, certain temperature, it's going to be red. When it gets hotter, it will turn to white, then to blue, and so forth. And we see this also reflected in the colors of stars up in the sky. But this is the color of the light emitted by this black body object. So in other words, these black bodies have a certain spectrum associated with them that's related to that. So the color that we see emitted is related to the frequency of the light. All right, so as we go from red to white to blue, the frequency is basically increasing as we go across this. All right, so this is one way that we can quantify, if you will, the colors. Now, another way we think of this is that these frequencies pass through different domains within the electromagnetic spectrum. So, for example, they may go from an infrared to an ultraviolet, to a visible first, let's do that, to an ultraviolet, to an X-ray. Okay, so in this case, the frequency is increasing as we move across here, and we're getting to faster and faster oscillating wavelengths of light. Well, according to classical physics, Rayleigh Jeans came up with a distribution law for the frequencies of black body radiation based on a certain temperature. And their distribution looks something like this. So this is a distribution of frequency at a given temperature. So we'll label it this way. And since it is a probability density, we got to put a little increment in frequency that this represents a probability density for. All right, and it turns out that I'm not going to go through the derivation, but it contains a lot of features, a lot of factors that we're already familiar with. It's basically 8 pi kb, where this is the Boltzmann constant, and T, which is the temperature, and this C down here is again the speed of light, but now cubed. Now their law said that this goes as nu squared d nu. All right, so what does that look like? All right, in order to get a picture of this going, let's draw over here. Okay, so we're going to draw nu on the horizontal axis and this probability density. And so what we're graphing here is basically this function of nu. Well, we know that y equals x squared is just the function, is just a parabola. So if we were to graph this out, we would see it go up something like this. And that's what that function, what that Rayleigh-Jeans distribution law looks like for the frequency of a black body. Okay, there's a problem with this though. And the problem is this, that when we actually measure the frequency distribution for a hot body, what we find is that it looks something like this. Okay, and you can see that while it's pretty good agreement down here, above that we have an area where things are not agreeing very well at all. In fact, they're diverging from one another. And since this is occurring at a higher frequency end of the spectrum, that's something that is, say, near the ultraviolet region of the spectrum. This is something that was called the ultraviolet catastrophe. Okay, and the ultraviolet catastrophe told people that there was something wrong with this formula. The problem was that a lots of people derived it and they got the same result. And so it wasn't something that was wrong with the mathematics that was used to get the formula. Something that was wrong was the classical assumptions that went into that. All right. And in particular, one of the assumptions that was really wrong was that energy was not continuous. Okay, that was a ground level assumption that went into the Rayleigh-Jeans law, but in fact it turns out that that may not have been the actual case. So in 1900, Max Planck, a physicist in Germany, was studying all of this, and he noted this ultraviolet catastrophe and said, you know, that maybe the thing that's wrong is this assumption that energy is continuous. So instead, what he said was that energy is discrete. Okay, now what does that mean? Well, he envisioned energy as being written something like this, where it's in discrete packets that have a collective energy of h nu, where h here is a constant that we'll define shortly, and nu is the frequency of the light, and the n is just some integer. So we can, we can collect a bunch of these packets of energy as we go along. And but what Planck did was to take this assumption and rederive the distribution law for the frequencies of a black body. And he came up with something somewhat different from what Rayleigh and Jeans came up with. His frequency law looked something like this. Okay, it had some of the same elements. So we had an 8 pi over c cubed, but he also had this h up here, the same constant that appeared here. And then over here, for the nu dependent part, instead of nu squared, it was nu cubed, and we had another factor of e to the h nu over kt minus 1 in the denominator. Right, now this is a dimensionless quantity, so we can actually check and see that the nu cubed replaces the nu squared, but h times nu is a quantity of energy, as is kt. So in effect, what we've done is we have taken kt and substituted h nu over this factor, okay, and basically made that substitution in this distribution law. Now, when you plot this distribution law out, you end up getting basically the observed spectrum of the black body. So in other words, Planck's law was spectacularly successful in predicting what goes on with black bodies and predicting this behavior. You'll get a chance to do some problems involving this Planck distribution law and black bodies, and to basically define where the maximum of the Planck distribution law occurs. Okay, so the net result of all of this, and I'll write a few of them down here. The net result is that light had energy in packets. And what this suggested was that light wasn't purely speaking a wave-like thing, but it might occur as some kind of particles which were called photons. So this is the first time that we had the use of the word photons to talk about this. And it turned out that this particular conclusion was something that also was associated with work that Einstein was doing around the same time, studying the photoelectric effect. And some people that are not physicists aren't aware of this, but in fact what Einstein won the Nobel Prize for was the photoelectric effect, was his prediction of photons as an explanation for a certain physical phenomena that involved ejecting electrons from a metal surface. Okay, not for relativity or some of the other great things that he did. And what Planck's development said was that each photon has this energy of h nu. So this is the energy of a photon, is this h nu. So this enables us to sort of quantify the amount of energy that's available to light based on its frequency. And ever since then, we have been measuring the frequency of light and the energy of light based on its frequency. Finally, this constant h is something that has the value 6.62607 and so forth times 10 to the minus 34 joule seconds. right? And this is something that is now known as Planck's constant, and it's a constant that we'll be using quite a bit in this course. All right, so it's one that you don't need to necessarily memorize it. You'll always be given its value. But it's an extremely important constant in quantum physics and in knowing something about the universe, in effect because it puts certain limitations on how well we can hone down our knowledge and the precision of our knowledge about matter that behaves as waves. All right, so that's a little bit of an introduction to what was wrong with classical physics at the turn of the 20th century and how Planck really made an incredible contribution to help straighten that out and to send us on the path of thinking about energy as coming in discrete packets as opposed to being continuous.